All right, so let's start by going over that problem that I mentioned from Wednesday's exam. That was a two-parameter family. Okay, I could put one like this on the final, but I'd probably change the function. F of x equals ax plus b over x squared. If I was going to be more precise about this, especially if I was going to use Mathematica, for example, maybe I'd put subscripts on the f, a and b. I could write f sub a comma b of x to emphasize this is a family of functions that depend on the parameters a and b. But just for sake of simplicity, I won't typically write that. What are you trying to do? You're trying to find critical point, the x coordinate, and the y coordinate of the minimum that it corresponds to. A and b are positive. And so the graph, when x is positive, actually you should be able to think about it just intuitively. You're adding a linear function, which is a graph that's a straight line with a positive slope, in fact, through the origin, plus b over x squared would be a function whose graph would go down like that. Adding two such functions would give you one still with the vertical asymptote near zero. And because b over x squared is decaying to zero, but ax is growing, it's got to eventually go back up again. That's got to be what the graph looks like. You can reason it out without calculus. So the question is, where does the critical point occur? X subcrit, and here in class I will go ahead and use the subscript notation, even though I did not do that. I said you did not have to use that on the test. And I label on the test that this depends on a and b. You didn't have to do that labeling, but I am, just to emphasize it. It does depend on what a and b are. As a and b change, this graph changes, and therefore the x location of the critical point changes. And it will be a minimum. And so I labeled the y coordinate, the value, the minimum value, I labeled it y sub min of a comma b, but again, you didn't have to actually use that labeling on the test. As far as big picture, what you do is the same thing you always do with optimization. Take the derivative, set it equal to zero, solve for the critical point. That's to find this. How do you solve for the minimum value once you get the critical point? Most of you knew the basic idea of it, at least even if the details were not so easy. How do you solve for the y min if you know x crit? By the way, I could have called it x min as well, because it is going to still correspond to the min. Just plug it into, most of you know what to do. Go ahead and say it. Plug that into what? It's on the sheet of paper somewhere. Plug it into the function, yeah, and then simplify. So take the derivative. 2 or 3 of you took the derivative as seeming incorrectly. It seemed like you were taking it with respect to either a or b, not x. When you differentiate with respect to x, treat the a and b as constant, that's going to differentiate to a. This one, you could use the quotient rule for, or you could recognize that it's b times x to the negative 2, which I mentioned, and you can avoid the quotient rule. The derivative is a minus 2b x to the negative 3. A and b are just constants. Set this equal to 0 and solve for x. Most of you, more than half of you got this part right. We can, for example, add 2b x to the negative 3 to both sides. It's probably beneficial to also write that as 2b over x cubed. I'm trying to solve for x, keep that in mind. So I'd like to isolate x. It's in a denominator here, so probably I should multiply both sides by x cubed and say divide both sides by a to rewrite this equation as x cubed equals 2b over a. Now take the cube root. X is going to be the cube root of 2b over a, which it's fine if you left the answer like that, but I was encouraging you by how I wrote the problem to write it in terms of powers of these things, because it helps you for the next part. This is the same as 2b over a to the 1/3 power. And then by properties of exponents, that's the same as 2 to the 1/3 power times b to the 1/3 power divided by a to the 1/3 power. And when you divide by a to the 1/3 power, that's the same as multiplying by a to the negative 1/3 power. So you can write your critical point like that. I'm not opposed to adding small things to problems on the final exam as well that were not on the original exams. And one small thing I could imagine adding to this is to say, yeah, this is a function of two variables, a and b. Wait a minute, I thought a and b were constants. Remember, as I've been saying in the entire semester, it's a big point for me. Whether it's a letter represents a variable or is a constant is all in your head. As I work through this problem so far, I'm saying a and b are constants. But here at the end, I see, hey, the answer depends on a and b. Why don't I think of a and b as variables? And I can, it's okay. And it's interesting and useful to do so sometimes. I might, for example, wonder how fast does this critical point x move, say, to the right as b increases? Maybe this would be a little question I would add to this problem, okay? It's related to stuff we've talked about before, so it would be okay. How would you do that? Well, what measures speed of something is the derivative, rate of change. What's the rate of change of this critical point with respect to b? Take the partial derivative of this thing with respect to b. There's the official partial derivative notation with the curvy d's. If you use regular d's, I won't count it as wrong, it's not a big deal. Though you should be aware, people typically use the curvy d's with partial derivatives, just to emphasize that there's more than one variable here. But when you do this derivative, you treat the a, the other thing, as a constant. Treat the b as a variable. And it would be fairly straightforward. You just use the power rule, bring down the 1/3 times the 2 to the 1/3 still needs to be there. Subtract 1/3 from the exponent. 1/3 minus 1 is negative 2/3. And keep the a as is. That would be the partial derivative of the critical point with respect to b. And so, for example, how fast is this moving to the right, say, as b increases, when a is, say 1 and b is 1? Okay, just to pick simple numbers. When a equals 1 and b equals 1, this equals 1/3 times 2 to the 1/3 times 1 to the negative 2/3 times 1 to the negative 1/3. Those are all ones. This is ultimately the cube root of 2 divided by 3. What is that approximately? Cube root of 2 is 2 to the 1/3. Divide by 3, that's approximately 0.42. What is that telling you? It's telling you how fast this point is moving to the right when a is 1 and b is 1 as b increases slightly from 1 to something slightly bigger than 1. What's the instantaneous rate of change? About 0.42. In other words, for example, if b increases from 1 to say 1.1, you should expect the critical point to move to the right when a is 1 as well by about 0.42 times 0.1 units, 0.042 units would be your approximation to how fast it's moving to the right, or how much it moves to the right if b increases from 1 to 1.1. Still interpreting the derivative as a rate of change. And we did have, I believe, a problem on exam 2 that was related to partial derivatives. Maybe my memory's faulty. I remember talking about it in class. I'm not ruling out adding a little bit to a problem like that. And so I'm telling you what to do right now if I did happen to do this. As far as doing the next part, I said, what is the minimum value? Y min of A comma B, and I told you what the answer was, so you just had to confirm it. You needed to plug X crit into F. It's a bit of a pain, but it's doable. You gotta go back up here into the formula for F and go ahead and use that form of the second term. Replace X with this thing. Yeah, that's nasty looking, but if you're careful, just take it step by step. So the formula for F is first A times X. So I do A times this thing. Plus B times X to the negative 2. So I get B times this thing to the negative 2 power. And then just be careful to use properties of exponents. For example, in this first term, the 2 to the 1/3 stays the same, the B to the 1/3 stays the same, but the A's can be combined. I can add the exponents. A to the first times A to the negative 1/3 is A to the 1 plus negative 1/3. In other words, A to the 1 minus 1/3, which is 2/3. And the B stays as a 1/3 power. Oops, I made a mistake here. That would have been trouble. This is a negative 2 power here. Raise this entire thing to the negative 2 power, and you have to negate all those exponents and also multiply them by 2. So the 2 would become to the negative 2/3 power, the B to the negative 2/3 power, and the A would go to the positive 2/3 power because it's already a negative 1/3. Simplify a little bit more. Combine the B's there. 1 minus 2/3 is 1/3. But then the question is how to combine these. One last step. If you didn't quite get this half step, I think this last step, I took off like half a point. How do you combine these? It's not so clear. Well, there's a few different ways you can do it. Realize that 2 to the negative 2/3 power is the same as 1 over 2 to the positive 2/3 power. In other words, this second thing can be thought of as a fraction. And then the only thing you can do really here is just try to combine these by getting a common denominator of 2 to the 2/3 power. So I got to multiply this thing by 2 to the 2/3 power over 2 to the 2/3 power. Combine those exponents, you get 2 to the first power. The denominators are now the same. And these then combine to give you 3 times A to the 2/3 times B to the 1/3 over 2 to the 2/3, which you can also write as times 2 to the negative 2/3 instead. Okay, so yeah, it was confusing, easy to make a mistake. But if you got the principles down and just do it step by step, you can do it.
For AX, would you parenthesize X and then distribute the A?
No, X is not a number. Well, okay, it is a number, but it's like here it's like a function name. So there's nothing you would have to do with this. Is that what you're asking about?
What I'm saying is when you first plug in X crit and X for the first part of the function AX,
Like right here.
would you parenthesize the 2 1/3 to 1/3?
Oh, this part?
Yeah, and then distribute the A?
You can put parentheses there, but if you don't have to. It's not really a distributive property in the usual sense. A distributive property is where you have, say, A times B plus C equals A times B plus A times C. Here, yeah, it doesn't hurt to put parentheses, but you don't have to put them. It's understood if you're doing all multiplications that you wouldn't need parentheses there. Okay. So, give partial credit. You know, if you had the basic idea right, but didn't carry out the calculations, I might have given you, how much was this worth? Only 3 points for doing this. I probably should have made it worth more, although then that would have penalized people if they didn't get it more. You know, if you wrote that down, I might have given you 1.5 out of 3 just to realize that's what you needed to do. And then just how far you got, it gives you another half point, then another half point, then another half point. Okay. And since it is tricky and easy to get confused, it's one of these situations where, like, if this is on the final exam, maybe it's good to go on to some other problem and come back to this later if you're afraid you're going to make mistakes or you're not sure what to do. Okay. It is important to think about strategies with test taking to make sure you don't get stuck on one problem too long. By the way, the final is not going to be a ton longer than the midterms. I think I've typically made the midterms worth like 4 or 5 pages of content. Maybe the final will be 6 pages. Okay, so and again, I'm not taking, certainly not taking all the old problems from all 3 exams. I'm taking samplings of them. And again, I don't even know which problems I'm taking yet. I'm probably going to have to do that this afternoon because I got to get ready before Monday. What else is worthwhile to do today? It's probably worthwhile to do big picture overview of the entire course. Not really to necessarily just help you in prepping for the final, but more importantly, and this really is more important than tests, is understanding what the class was all about, right? So, you know, final exam is more important for your grade, but big picture idea is more important for your long-term future if you ever need calculus in the future. And again, remember I said don't sell yourself short. You might think this is your last math class ever and you'll never need calculus again. Well, you really don't know for sure. You might be in a job situation where maybe you need to use some data science, right? You know, the fact that you're in this class does mean you may feel like you're not good at math, but you probably are better than the average person out there being in a calc class. And so people might look to you to help with math, and maybe you need to learn some data science as an example of something you might need to learn to help a colleague who's doing something with statistics, for example. Or to, if you're not helping them, to understand what they're doing. You want to understand what they're doing because maybe it'll help you understand what you should do, even if it's not as mathematical as them. And you want to understand their presentations they might give, that kind of thing. Maybe you're their boss. And, you know, people give presentations to their bosses and you want to understand what they're talking about to some degree. So maybe you need to learn it in a little data science, and so maybe you need to learn about it online, and maybe some part of data science, as does happen, does involve calculus. Okay, and so that might mean you need to review calculus, and so getting a big picture overview is a good thing. I'm not going to list out topics by chapter like I've done before previous exams, but maybe what would be good is to still do some things in the approximate order that we've been doing. And one thing that might be good actually is to talk about an application I've hinted at, but I haven't talked about a ton. Thought of, say, a mass on a spring. And to keep things as ideal as possible, we're trying to minimize friction, essentially assume there's no friction. How do you do that? Well, maybe this is ice down here. This is a wall over here. Got the mass attached to a spring here, block of wood on the ice. And if you want to minimize friction even more, we better be in a vacuum. Okay. Yeah, when would you ever do this? Well, probably never, but we can imagine doing it. And it's a useful thing to imagine. There still would be friction, right? Because you wouldn't be able to avoid the friction that would come from the molecular interactions in the spring itself. That would cause some friction. So you can't really completely avoid friction, but you can try to minimize it. And you might be able to minimize it to the point where simple harmonic motion is a decent model of this. Back and forth motion, grab the mass, pull it, and let it go from rest, say. So it's going to go back and forth, and The simplest model for that is trig functions, cosines and sines, or maybe some combination of them might be a decent model for the motion. Okay, and we'll try to keep it simple here. Let's say the motion is that the x position here is horizontal. You can do it up and down as well. The x position of the mass is given by some cosine wave. Maybe 2 times cosine of, just to pick something here, maybe 7 pi over 2 times t, where t is time in seconds, and x is position. Let's go ahead and use meters. If this is going to be meters, though, it's going to have to be a big mass and a big spring, and it's moving back and forth pretty wildly. And we could give this function a name, call it, say, f of t. That could be an example that might describe the motion. In fact, it would describe the motion if we pull the mass 2 meters to the right. This is representing position, not distance. And that means there's got to be some, if it's going to be this kind of formula where it can go positive or negative, there's got to be some spot where it equals 0, which would be the equilibrium position of the mass in the spring where it doesn't move. I could pretend it's right where it is in the picture, the center of mass right there. I could pretend is x equals 0. So this is not the origin over there. This is the origin over there. It's convenient when you're solving physical problems like this to choose the origin to be at, well, in this kind of situation, the center of mass when the mass is at rest. And then you imagine pulling it to the right, say that's the positive direction, 2 meters. When t is 0 here, cosine of 0 is 1, and so you get 2 times 1 is 2. So you're doing it 2 meters to the right. Am I letting it go for rest from rest or not? Do you have a guess? Based on this function, am I letting it go from rest, or am I like hitting it with a hammer or something and giving it some initial velocity? You should be able to guess based on the imagining the graph of that function. Anybody have a guess? And if you have a guess, why? Do you have a guess?
Set release because there isn't any sort of there isn't any sort of constant in there.
I didn't quite catch the very first thing you said.
I thought it was just releasing it.
It is releasing it. That's right. That is correct.
Because there isn't any sort of constant that was shifted horizontally.
Okay. And related to that fact is the fact that the graph of cosine starts at the peak at t equals 0 and also has a 0 slope at t equals 0. Just a plain cosine with, yes, no horizontal shift. The graph of x versus t is going to look like a cosine wave. Its value at t equals 0 is 2 times 1 is 2. It will have a horizontal tangent. That's where calculus starts to come into play here. A horizontal tangent line at t equals 0. Because we know that about the graph of cosine, that has not been had a horizontal shift. And it oscillates with a certain period. Remember how to find the period? Period, call it capital T. Remember how to do that? It's a fraction. Nobody? Want to say? 2 pi on top and whatever's in front of t on the bottom. Technically, the technical name for that is the angular frequency. So you might wonder, where is there an angle? Don't worry about it. You can simplify this. The pi's cancel. 2 divided by 7/2 is the same as 2 times 2/7. This is 4/7 for the period. 4/7 seconds. About, what would that be? 0.57 or 58 seconds, I think. A little over half a second. So how fast, it's a 2 meter amplitude of a 4 meter max to min oscillation. That's moving pretty fast. I wouldn't want to be in the way of this mass, especially if it's massive. Moving pretty fast. I mean, it's not as fast as oscillations of sound waves and light waves.
That's something like 7 meters, about 7 meters per second on average.
Is it? Okay. Yeah,
You said
okay.
4 meters in 4/7 seconds.
It's it's actually going to go 8 meters in 4/7 seconds because it goes back and forth.
That is incorrect. 14 meters.
Okay.
On average.
Yeah, about 14 meters per second. That, I don't know if I can run faster than that. Maybe. I'm not sure. 14 meters per second. I don't think I can run faster than that. No. Although it does speed up and slow down, right? Think about it. You're letting it go from rest because the initial tangent line has a slope of 0. It speeds up pretty quickly as it passes through the equilibrium position. It's got to slow down as it approaches the wall because the spring is now starting to push the other direction. It's being squashed, so it's giving a restoring force in the other direction. And it's got to turn around, so there is another moment in time where its instantaneous velocity is 0. And then it speeds up in the rightward direction. And it's going to go back and forth. And if we've set it up right, evidently it's not hitting the wall. The spring's not breaking. It's a model. It's not perfect. One way it's not perfect is because of friction. Another way it's not perfect is because, well, if we pull the mass too far, the spring could break. And then this function wouldn't work at all, probably. How would the 7 pi arise? You know, where 7 pi over 2, the b in front of the t, where does that come from to make the period 4/7? It's got to be related to the spring and maybe the mass itself. If you've got a stiffer spring, stronger spring, you might say, that has a stronger restoring force, should be a faster oscillation. Doesn't that make intuitive sense? Which would make a smaller period, higher frequency, smaller period. And if the spring were not very strong, you know, if it could barely even pull the mass, that's going to be a slower oscillation, a smaller frequency and a larger period. So fast oscillations have faster frequency and faster angular frequencies. Slow oscillations have smaller frequencies and angular frequencies. But I'd call this the angular frequency. By the way, the exact frequency in units of 1/seconds, which is called hertz, is just the reciprocal of the period, 1/t, and that'll be 7 force hertz Hz. But, you know, that's compared to a sound wave or a light wave, that's a very small frequency, right? Sound waves that we typically can hear are hundreds of hertz, maybe into the thousands of hertz. And light waves, I don't know offhand, millions of hertz, something like that. Depends on what kind of light wave it is, or what I should really say, electromagnetic radiation. What is it? Things like X-rays and so forth are high frequency, and infrared, for example, radio waves are low frequency. Anyway, coming back to thinking about calculus, what's the derivative of this function? Dx dt or f prime of t. Well, you know how to differentiate something like that. We need the chain rule. The 2 is just going to stay there. Derivative of cosine is negative sine. The input would still be the same, 7 pi over 2 times t, but then by the chain rule, multiply times the derivative of the inside function, 7 pi over 2 times t. The derivative is 7 pi over 2. Simplify, the 2's cancel. I can write the derivative as negative 7 pi sine of 7 pi over 2 times t. This is going to be a much bigger oscillation in this function. 7 pi is about 20, real close to 22. This is very close to negative 22 sine of 7 pi over 2 times t. A sine wave with an amplitude of 22, that sine of t is 0, so it's initially going to go through 0, but it's going to go down very rapidly. I'm not going to draw the whole thing here. Would go way down off the paper even. Before coming back up pretty rapidly to 0 again. Before going up positively and coming back to 0 at 4/7. The period is the same. It's just that the amplitude is much bigger. Can we physically see this amplitude? Well, only in the sense that the velocity gets large in magnitude. In fact, 22 meters per second is the maximum velocity. The amplitude is the same as the maximum velocity. This is the velocity. And I should call this a velocity, not a speed, because it can be positive, it can be negative. This is back and forth motion. If I'm saying positive x-axis is to the right, so these are positive positions over here and negative positions over here, then when the mass is moving to the right, that's a positive velocity, and when the mass is moving to the left, it's a negative velocity. When I let it go from rest, its initial velocity is 0, but it quickly becomes negative because it's moving to the left. And the units would be meters per second. If our yes was after the speed, which I could call speed of t if I like, that would be the absolute value of the velocity, absolute value of f prime of t. Absolute value of this, which technically speaking, you cannot write without an absolute value sign unless you wrote it in a piecewise way. It would be 22 times the absolute value of sine of 7 pi over 2 times t. You'd take the green graph up there and you'd have to, the part that's below the t-axis, you'd have to reflect across the t-axis. So it'd go up like this before coming down. And there would be a place where the speed function is actually not differentiable. There'd be a corner in the graph right there. The velocity is differentiable, but the speed is not. Interesting. Possible to make sense of. Well, it's difficult, I think. You can also compute the acceleration as a quantity that can be both positive or negative. The acceleration is the derivative of velocity. You can also say it's the second derivative of the position. F double prime of t. You would get yet another factor of 7 pi over 2. The sign would change to a cosine. The negative sign would still be there, right? Because the derivative of sine is cosine, so the derivative of negative sine is negative cosine. In exact form, we get another factor again of 7 pi over 2. So we'd have 49 pi squared over 2 cos 7 pi over 2 times t. That would be a formula for the acceleration function. The amplitude of this function is even larger. 49 times pi squared over 2. The acceleration has a maximum value of about 241.8 meters per second squared. That's kind of hard to visualize. I mean, you can draw the graph of it, but physically seeing that acceleration, you can't, it's pretty much impossible other than just to say it gets real big. The mass is moving pretty quickly, pretty far, it is speeding up and slowing down a lot. Or you might say very rapidly and with large accelerations in absolute value. Is there a name for the absolute value of the acceleration? I don't know, maybe absolute acceleration, I'm not sure. So that's related to derivatives and slopes of tangent lines. The green graph is telling you slopes of tangent lines to the red graph. You could draw a bunch of slopes of tangent lines and imagine estimating their slopes. And if you did visually estimate them, you would get the values of the green graphs. And for example, where the green graph is 0, that's where the red graph has horizontal tangents. Critical points of the red graph are where its derivative, the velocity, is 0. And you could think about this in terms of the first or second derivative test. You could say, hey, the green graph, the velocity changes from negative to positive as t increases through 2/7. Therefore, the red graph has to have a minimum because its slope is changing from negative to positive. That's the first derivative test. What's the question? Yeah. So you could also think about the second derivative test. For example, if you plugged in t equals 2/7 here, imagine with me, 7 pi over 2 times 2/7. The 7 and the 2's would cancel. You get pi. Cosine of pi is -1. So you have negative 49 pi squared over 2 times -1 is a positive number, telling you the red graph's concave up near 2/7. That's it. That would be the second derivative test to confirm that's a minimum. You could also think about this stuff in terms of integration. You could think of it purely in terms of antiderivatives, for one thing. Let's think about it with the velocity and position. You could say that, for example, x is an antiderivative of the velocity. The velocity was -7 pi sine 7 pi over 2 times t. And with a little bit of experimentation, even if you hadn't solved the first problem of finding the derivative of x with respect to t, you could eventually realize that this is going to be cosine, 2 times cosine of 7 pi over 2 times t plus c. And the c would be determined by the initial position. If I wanted the initial position to be 2 meters, like I did, I'd say 2 equals x of 0. I'm being a little sloppy with my notation here. I'm treating the x here as both a variable name and a function name. That's technically not ideal, but people do it. I could also call this f of 0. Plug in 0 and solve for c. Cosine of 0 is 1, so this becomes 2 plus c. And therefore, c is 0 if I want this to start at position 2 when t is 0, which is what I did before. But if it was a different position when t is 0, and I still had the same velocity, I'd get a different value of c. For example, if I wanted to start at position 3 when t is 0, I'd make this a 3 there, and then the c would have to be 1. That would be a possible answer. However, there is a catch with that one. It would no longer actually fit the model of a mass in a spring. So it wouldn't be a valid model to do that. Because the graph would not, of this x graph would not be centered at x equals 0. It would be shifted up by 1 unit, and that would not work for a mass in a spring like this, unless you changed where 0 was. But that's kind of silly. Okay. Is there a question, Michael?
No, I was just thinking of a way to make it work. This is the velocity graph, right?
Well, this function here is the position.
Position, never mind.
Yeah. I integrated the velocity. This was the velocity. By the way, An interesting kind of symbolic jujitsu I could do here is I could write this integral as the integral of dx dt, and I could pretend that I can cancel the dt's and write this integral as the integral of dx and say, effectively, to find x, I need to integrate dx. I need to add up the little changes in x to get the total change in x. If that's confusing, ignore it, but you'll see it come up in science textbooks. It's not rigorous math, it's hand-wavy math. Okay. Could I relate it to definite integrals? Yep. I could also, for example, say that x, I'll go ahead and write in f of t here. X equals f of t. If I wanted to start at position 2 when t is 0, I could do this. I could write a 2 plus the definite integral from the starting time, which is 0, to an arbitrary time t of the velocity function. But if I do this trick, I should use a different letter, like you say, a dummy variable. Again, in science and engineering classes, they often don't bother with the dummy variable. They'll put a t there as well. But I'm saying, ideally, it's good to be precise here and emphasize the variable for this function is in this upper limit of the integral. And this does still satisfy the model. And if I plugged in the velocity, it would work. It is another way to represent x. And I also can think about this in terms of that second fundamental theorem of calculus. I could say the derivative of x with respect to t, or f prime of t, is the derivative with respect to t of this entire thing, including the plus 2. The plus 2 there is just, it's put there to make the initial position 2 when t is 0, because when t is 0, the integral is from 0 to 0, which is 0. 0 plus 2 is 2. So having the 2 plus there at the beginning makes this have the right initial position. But when you differentiate 2, you get 0. And when you differentiate the integral by the second fundamental theorem of calculus, it's like you can pretend the ddt and the integral sign cancel, and the du goes away as well, and you're left with the function b. But don't put a u here, put a t. Right? We've emphasized this a lot recently. U's name doesn't matter, t's does, because I want the t here to match the t there. I also want it to match the t there and the t there. Those all have to be consistent with each other. So I better put a t there. It would be wrong to put a u. So emphasizing the fundamental theorem of calculus in the second form as well. And we could do definite integrals to find particular values of x if we wanted to. If we didn't know the formula for x was this, we could even numerically integrate it with the left-hand sum, right-hand sum, and trapezoid sum. That's the average of the two. If we didn't know the formula for these things. If we didn't know this formula, but we knew this formula, but we weren't sure how to do this symbolically, we could approximate the answer with summations. Now it's good to realize, because sometimes this function might be complicated enough that you can't do it symbolically. Because one of those other functions, Fresnel's, Earth, etc., there's hundreds of others, could come up and you wouldn't know what it was. So you'd have to do the integrals numerically, do approximations. And it's also true that you can interpret it graphically. The green graph tells you the slopes of the red graph. Areas between the green graph and the horizontal axis tell you how the x graph changes. For example, if I imagine time going from 0 to, say, I don't know, 0.02 or something, that area counted negatively towards the integral would tell you how much x changes from time 0 to time 0.02. What's the change in x? I call it that delta x. Delta x here, if I wanted to actually compute how much it changed, if I didn't know the formula for x, I could integrate the velocity from 0 to 0.02. And if I needed to, I could do an approximation to the integral with a summation, effectively finding this area and negating it because the graph is below the axis. It would be a negative answer. This is going to be a negative number, indicating x is going down, indicating the mass is moving to the left. The position is decreasing when you're moving to the left. You could talk about optimization. You could try to optimize the velocity and acceleration. Everything is tied together is what I'm trying to emphasize. I will also say here that calculus is useful in this situation for a more general approach to this kind of model that could take, for example, friction into account, and also could take what's called external forcing into account. What kind of external forcing? Well, if this ice is on the top of a table, if it's a big block of ice on the top of the table, you could set some mechanical thing up where something's grabbing the table and oscillating it back and forth like this as time goes by. That would be an external forcing function. That would definitely affect the motion. It would not be so simple anymore. In fact, I'll even give you a little preview if you're going to take diffie-q or diffie-q with linear algebra. Sometimes, if you do it right, the motion can be something more like this. Small oscillations at first, then they get bigger and bigger, and then they get smaller and smaller again, then bigger and bigger again, then smaller and smaller again, then bigger and bigger again, then smaller and smaller again. The graph of x as a function of time in that kind of forcing function situation could look like that. This is called beating. And in physics, you might have encountered this when your physics teacher maybe had two tuning forks that were slightly different notes. And you hit both of them, and the sound waves you hear, they get louder and softer and louder and softer and louder and softer. You're hearing this kind of thing. This is near resonance is another way to say this. And yeah, you're hearing beats, a beating in the sound intensity. So the calculus, through differential equations and things like Newton's second law in physics, can help you come up with more complicated models to model more complicated situations. And it's not that the model is perfect, again, but oftentimes it can be pretty good. And if it's pretty good, then it might be useful. You wouldn't want your shock absorbers in your car to do this kind of thing, right? More easily break. So then the question becomes, an engineering question becomes, how do you design your shock absorbers to avoid this kind of thing happening? And they do various things to the shock absorbers to do that. I think, I'm not an expert on it by any means, but I think I've heard they put special fluid inside the shock absorbers whose viscosity changes as the speed of the shock absorbers motion changes, and therefore it affects how much they oscillate and that kind of thing. Okay, it's all the math and science can then be related to engineering, designing shock absorbers, designing bridges. Right? Have you seen the videos of the Tacoma Narrows Bridge from 70 years ago collapse because wind caused the oscillations in the bridge to be too big? It's pretty amazing. You should look for it if you've never seen it before. Look up.
It's actually pretty amazing how how much wobble it takes to make that. pretty
Yeah.
well.
Yeah, it's actually designed pretty well, huh? That way. And it doesn't just wobble up and down, it also, there's other effects that cause it to sort of twist. So I think part of that is just that the wind is kind of, it's not really a steady forcing function. Other kinds of models you could do is attach so this mass is attached to a wall that you can't move by a spring. You could attach another mass to this mass with another spring. And then you got both masses moving back and forth. The model gets harder, the math gets harder, but it still can be done. Of course, in real life, you have to worry about the masses colliding and that kind of thing. And so yeah, that could wreck the model, but okay. That's big picture. I think that's mostly what I wanted to say. Let me just say a few more things about what to expect in Calc 2 if you're going to take Calc 2 in the spring. And then you can go. So we essentially, went through much of chapter 6 here, though I didn't assign homework from chapter 6, except, well, I guess there were a few problems from chapter 6. Sorry. What I do in teaching Calc 2, starting in February here, is that we review chapters 5 and 6 to start with. And that's, I think, a very good thing to do. But we do review it pretty quickly, like within 4 or 5 class periods. Review chapters 5 and 6. In addition, doing a chapter we skipped, a section we skipped was section 6.3 on differential equations. And motion, there's motion. And then the other chapters that we get to in Calc 2, we start with chapter 7, which is about techniques of integration, which David was talking about a week ago or so, wondering, are there methods like for derivatives, there's the product rule, quotient rule, chain rule, are there for integrals? And he said, yes, there were, and yes, there are. Integration by substitution is one of those methods. Another method is called integration by parts. Partial fractions is another one. Special formulas is another one. There's just various special formulas that are worth memorizing. Those are the main tricks, you might say, for doing integrals. Integrals definitely are harder than derivatives. They take a lot more practice. Gateway exam is harder. We do know more about numerical methods for integration, approximating integrals. Better methods than the left sum, right sum, and trapezoid are called midpoint rule and Simpson's rule. Ultimately, simp here is called Simpson's rule, and that gets you very close to the value of the integral for relatively small values of n. Improper integrals, we bring infinity back into play with those. Those have lots of applications to physics and engineering and probability, especially. Chapter 8 is about using integrals. So there's lots of applications in chapter 8, some of them which are geometric, finding volumes, for example. Some of which are physics, like centers of mass. Some of which can be anything, like statistics. Probability and statistics are other applications. There are applications in here to economics as well. That's probably through chapter 8. It's not that it's easy, but it's probably the easiest part of Calc 2. Once you get to chapter 9, it gets, for most people, it gets harder. Sequences and series, and also something called Taylor series, which people typically have a harder time with. Essentially, series are infinite summations. You're adding up infinitely many numbers, which sounds like impossible. How could you add up infinitely many numbers? Well, the limit concept comes into play yet again. Sequences, series, Taylor series, and we wrap it up pretty much with chapter 11 for the most part. More about differential equations in more depth is chapter 11. And I do try to weave in more multivariable calculus as well. More about functions of two variables and partial derivatives, and more about even integrals in such situations as well, to help prep you if you needed to take multivariable calculus. Okay. Do you have any questions? That's a quick overview of what to expect in Calc 2. Question?
So the PSGO, should we keep our books for next semester?
Yeah, if you're taking Calc 2 next semester, keep your book. Yep. Use the same one, although make sure you got at least through chapter 11. which you should, I think I set it up that way. With the loose leaf. This one automatically goes to chapter 11. Anything else? All right, see you bright and early Monday morning. Thanks for being in the class. We'll see you then.